Hey, good morning, all you MRWC fans. This is Mr. Ainsworth. We're going to get into your Theme 1, Section 2 review here to get ready for our exam, okay? So it's next week, so let's do our best. Have your section notes out and have your pencil, red pen, highlighters, all that good stuff. I'm going to annotate the important points. All right, so let's start off with probably one of the biggest themes in the section, since it's all about rational numbers, and talk about rational form, okay? Get out your red pen for this. What is rational form? Well, as you guys know, that it can be written as a fraction. It looks like a divided by b, okay, where a and b are integers, okay, and b is not equal to 0. So basically you have an integer over an integer. This is rational form, okay, where a and b are elements of the integer set, z for Zollen, okay, or you can say integers. Okay, and b is not equal to 0. Okay, you can't divide by 0. It's a no. Okay, so a and b are integers. So when you have an integer over an integer, you have a rational number. Okay, so some examples like 2/3, that's rational. 10, which is 10 over 1, that's rational. All right, not equals. Negative and negative numbers are rational too. So like negative 4/3, that's rational. 0 is rational. 0 can be written as 0 divided by 2. That's still 0. Okay, so all of those numbers, any number that can be written as a ratio of two integers, okay, like a fraction like this, is a rational number. So that's rational form. Let's highlight that. That's really big. All right, so in number 2, okay, which ones are rational? It says simplify. Okay, that's number 1. And then which ones are irrational? Big question. All right, so here we go. Let's go for it. So log base 2 of 32. Okay, so to answer this, you got to be thinking, okay, 2 to what number, 2 to what power is equal to 32? Okay, you got to be thinking that. 2 to what power equals 32? So if you do powers of 2, 2, 4, 8, 16, 32. These are called powers of 2. This is 2 to the first, 2 squared, 2 cubed, all right, 2 to the fourth, 2 to the fifth. Whoops, sorry. Let me fix that. 2 to the fifth, okay. These are called powers of 2. So 2 to the fifth is 32, so this answer is 5, and guess what? That is rational, okay. Why? Because 5 can be written as 5 divided by 1, and it's a rational number. That's why. So that's rational. Even though it's a log and it looks kind of crazy, it is rational, okay. But is log base 9 of 3 rational? Well, let's see. Okay, so we got to be thinking 9 to what power, that's a question mark, is equal to 3. All right, and we know that the square root of 9 is 3. We know that. Okay, so the square root of 9 equals 3. And we know that the square root of 9 can be written as 9 to the 1/2 power. Okay, so this is actually equal to 1/2, and that's rational. Okay, so this is rational. This one's rational. Why? Because they can be represented as a ratio of two integers, like a fraction, a over b, an integer divided by an integer. That's why I started off with rational form, because, that's the first thing you have to decide is, are these rational or are they irrational? One of the two. The next one can be written as 1 over 3 cubed, just using basic laws of exponents right here, and that's 1 divided by 27. And that's because 3 times 3 times 3 is the same thing as 9 times 3, and that's the same thing as 27. Okay, so that's rational too. Now, not all numbers are rational, okay, but so far these are. Now, is D a rational number? So I don't know, you got to simplify it, right? So 27 is 9 times 3, so the square root of 9 times the square root of 3 can be written as 3 root 3. So obviously I'm simplifying here. The square root of 12 is the square root of 4 times the square root of 3, which is 2 rad 3. And 48, let's factor 48. Okay, so 48 divided by 2 is 24, divided by 2 is 12, divided by 2 is 6, divided by 2 is 3, and divided by 3 is obviously 1. Okay, so I see the factors over here. I see 2 to the 4th times 3. This is called prime factorization. Prime factorization. You get the idea? All right, and that's 16 times 3. So all of this is equal to 16 times 3. which is 48. So minus root 16 times root 3, which gives you 4 root 3. So when you're all said and done, 3 root 3 minus 2 root 3 is 1 root 3. So you get 1 root 3. Minus 4 root 3 is a negative 3 root 3. Okay, and so let's highlight that. So that right there, the square root of a prime is always irrational. So that's irrational. All right, so this is irrational. So it's not rational. We say irrational. All right, we're rocking. Okay, so now E here. Let's make a little note here. I don't have room right here, so let's go up to the very top. Okay, so let's make a little note. So these guys right here, these are decimals. Okay, and any decimal. We talked about this in our activity 2D2 here. Any repeating decimal or any decimal period, all right, can be written in rational form. So any decimal, all right, can be written in rational form. We talked about that in activity 2D2. So activity 2D2, okay, you got to refer to that. All right, because of that, both of these are rational. So this is rational, and this one is too. I'm not going to do this right now. We got number 3 to talk about. So F here, 0.93 bar or 0.93 repeating, will be discussed in number 3. All right, but that's activity 2D2. So refer to activity 2D2, which is the previous one here that we talked about. Where I discuss how to change a repeating decimal to a rational number, okay, a fraction in the form of an integer divided by an integer. All right. So speaking of that, let's do it. Okay, so one of the methods, one of many, to convert a repeating decimal, all right, to a fraction, okay, right here, to a fraction, is by using what's called infinite geometric series. So in number 3, parts A and B, we're going to use this technique. Okay, there's more than one technique. So we're going to expand the decimal as an infinite sum of decimals, and then we're going to express it as a sum of fractions, and then we're going to use the formula, all right, this formula here, S is equal to A sub 1 divided by 1 minus R, to figure this out. We're going to use this infinite sum formula to find an equivalent fraction. Okay, now this is activity 2D2, as I just said earlier. So obviously, whenever you review, all right, have your notes handy, guys. Have all your activities handy. I mean, it's called being ready, okay? Have your notes ready, all your activities. That's what good students do. All right, so here we go. We're going to expand it first. So this decimal is 0.07 repeating. So I'm just going to expand it. Okay, and then I'm going to decompose it into its parts. So here we go. So 0.07 is its first part. Second part is 0.007. Third part, let me switch colors here. So the third part here, this one in green, it's the fourth digit, so plus 0.0007. You need 3 digits or 3 placeholders before the fourth digit, so just keep that in mind. All right, and the fifth digit right here, you got 4 digits preceding that, so you're going to need 4 zeros, so 1, 2, 3, 4, and then go dot, 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 okay, plus, this keeps on going. So I'm going to go to fractional form. So here we go. So 7 100ths plus 7 1,000ths. You have to understand place value. So again, here we have 3 digits in the number, and notice that we have 3 zeros in the fraction. I'll talk about that here in a minute. Then we have 7 10,000ths, and then we have 7 100,000ths, plus a bunch more. Okay, so one more time. Watch this. In 0.07, there's 2 digits, and notice there's 2 zeros in the 100. Next one, there's 3 digits in the 0.007, and notice there's 3 zeros in 1,000. It's just an easy way to keep track of your zeros in your denominator. And then in 0.0007, there's 4 digits total, and notice there's 4 digits in the denominator in 10,000. And the last one, you just count 5 and 5. Okay, so it's not that difficult. All right, so here we've got A sub 1 is your first term, okay? And the common ratio, R, is 1/10. You multiply by 1/10. Okay, so again, refer to your activity. You can see that. So a sub 1 is your first term. Okay, and that's obviously right here. 7/100ths. You know the common ratio, and here we go. Let's get started. Okay, so S is equal to the a sub 1, which is 7/100ths, divided by 1 minus 1/10. That's the same thing as 7/100ths divided by 9/10. So S is going to be equal to 7/100ths times the reciprocal, 10/9. You got to multiply by the reciprocal there. Then you got to simplify, divide both of these by 10. And you're going to get, let me see, 7 times 1 is 7, 10 times 9 is 90, and you get 7/90ths. And it'll probably be good for you guys too, also to, use a calculator and verify that. So if you are worried about the 8 there, the calculator rounds up. When the last digit is greater than 5 or greater, you round up. Okay, you just use the rounding rule. So this is the same decimal, 0.07 repeating. So we're good. Okay, so this is equal to 7/90ths, and it's a rational number. That's our result. So we found an equivalent fraction for the repeating decimal. Any repeating decimal or any decimal period can be written as a fraction. Let's make a note of that. I said that earlier at the top. Okay, any repeating decimal or any decimal period, actually, okay, all right, can be written as a fraction. And that's what activity 2D2 is about. It was about showing you guys how to do that using what's called an infinite geometric series. There's more than one way to do this. There's other ways too. All right, we'll explore that later. Right now, we're just focusing on that technique. Now, this one here, we got 0.24242424. It's repeating, right? And it's infinite, so dot, dot, dot. Okay, let's break it up, decompose it. So 0.24 plus 0.0024 plus 0.000024. Again, so you got first group, second group. So you got first group here. Second group of digits is here. Okay, so remember that notice it's 4 digits. Okay, and then the third group is here, but remember that's the 5th and 6th digits. So notice that you have to have 4 zeros as placeholders. So, and then this goes on and on. Dun, dun, dun. Okay, so now you convert to fractions. So 24/100ths, 24/10,000ths. Again, 4 digits, 4 zeros. And then you got 24, let me see, thousands, 10,000s, 100,000s, millions. So you have to have 6 digits. So 6 zeros. That's 24/1,000,000s, dot, dot, dot. And then you go for it. You got, well, let's determine this. We have first term. Okay, so we have, this is your a sub 1. And your common ratio is not 1/10, it is 1/100th. Okay, so you multiply 100 times 100, you get 10,000. But these are fractions, so you have to multiply by 1/100th. So R is 1/100th in this example. A sub 1 is obvious, it's the first term, so it's 24/100ths. And at that point, you just go for it. So let's go for it. So S for sum, you got A sub 1 divided by 1 minus R. And here we go. So we have A sub 1 is 24/100ths. And then we've got the 1 minus the common ratio of 1/100th. Be careful here because it's a little bit different than the previous one because we have denominator of 100, not 10. So we have 24/100ths divided by 99/100ths. You take out 1 from 100, you have 99 remaining. And then you have 24/100ths times the reciprocal, 99ths, excuse me. Simplify and you're done. Okay, so just divide here and you get 24/99ths. And so this fraction here, this repeating decimal, is actually equal to 24/99ths, and you can check it, and you should. Okay, so 24 divided by 99. Okay, notice that you get the same decimal. So 0.24 repeating is actually equal to 24/99ths. Okay, so we used an infinite geometric series to find an equivalent fraction, which means that any repeating decimal can be written as a fraction or as a rational number. Okay, so therefore it's rational. Okay. Now this is a video, right? So make sure that you guys use it properly. Meaning that if I'm going too fast, which I probably am, rewind it. Pause, play, rewind. Okay, now the other one. This is a previous activity here. Use prime factorization to determine whether decimal equivalents will either terminate or repeat. Okay, so a little key point here. Oops, sorry. So if a decimal terminates, a little note. So terminating decimals, okay. For terminating decimals, when you factor the denominator of the fraction, the only factors are allowed are 2 and 5. So for termination, this is point number 1. Okay, so for termination, only factors are allowed are 2 and 5. Only factors are allowed are 2 and 5, basically. Okay, if you have any other factor, then it's going to repeat. Okay, so what we need to do is factor the 60 and factor the 160 and see what's going on. Okay, so let's do that. So let's factor 60 here. So 60 divided by 2 is 30, divided by 2 is 15, divided by, not 2, it's not even, divided by 3 is 5, divided by 5 is 1. So right here, this is 2 squared times 3 times 5. These are the prime factors. So this is equal to 1 divided by 2 squared. 2 squared times 3 times 5. And because of the 3 here, because of this factor of 3, okay, this fraction is going to repeat. Okay? So I can verify that. So all you have to do is take 1 divided by 60. So 1 divided by 60, and you can see what I'm talking about. Okay? So it's 0.016 repeating. So this is equal to 0.016 repeating. It repeats. Why? Because of the 3. So highlight the 3 there. I don't know why my screen keeps doing that. So sorry. So what we have, let's factor 160 now. So let's do some homework. So 160 divided by 2 is 80. Divided by 2 is 40. Divided by 2 is 20. Divided by 2 is 10. Divided by 2 is 5. Divided by 5 is 1. So it's 1, 2, 3, 4, 5. So this right here is equal to 2 to the 5th times 5. So we get 1 divided by 2 to the 5th times 5. And notice the factors, okay? I'm talking about the basis. So the prime factors, you can even see right here. So let's highlight them. The only prime factors are 2 and 5. And right away, I know that it's going to terminate. So prime factors are 2 and 5. So it terminates. And we know what it terminates in because we look at the highest exponent of the prime factors. So let's highlight the 5. Okay, so it terminates right there. It terminates after 5 digits. So after 5 digits, and I'll show you. Okay, so it terminates after 5 digits. Just by looking at the exponent, okay? Right up here. All right, let's check. All right, take 1 divided by 60. Excuse me, 1 divided by 160. 0.0065. So this is equal to 0.062. Oops. Here we go, 5 digits. Now, I think this was activity 2D1. Let's see. Yes. Okay, so this is activity 2D1. So let's make a little note of that. Okay, there we go. All right. Okay, now this is again a review. That's why I said take your notes out, refer to them, because guess what? We did this before. We did all of this before. None of this is new. All right, but again, you got to get good at it, right? And the way you get good is by practicing. Okay, now this is the second method, how to convert a decimal to a fraction. All right, irrational form here. A rational number. Okay, don't use the infinite geometric series approach. Okay, so there's a way to do this. So let's say you're given this fraction. It's 0.9 repeating. And when I first saw this back when I was a kid, I was blown away. It was kind of amazing here. So let's call this number n here. Let's just give it a name. So 0.9 repeating. Let's call it n, and only one digit repeats. So what I'm going to do is I'm going to multiply both sides by n, and you could do that in algebra, right? Given any equation, you can multiply the equation by whatever factor you want. Okay, so I'm going to multiply it by 10, both sides. So I'm going to have 10n up here and put it above. Okay, and when you multiply the fraction or the decimal by 10, you shift the decimal place to the right one place. So you're going to get 9.9 repeating. Okay, so when multiplying by 10, you shift the decimal right one place. Well, then let's do this. Let's get a little creative here. Okay, we're going to subtract. And what we're going to do is we're going to subtract both sides like we normally do. So 10n minus 1n is 9n. And then when you subtract your decimals, okay, well, guess what? These cancel out and you get 9. Okay, so 9n equals 9. And then you divide both sides by 9, obviously, or just think about it. 9 times what is 9? And the answer obviously has to be 1. So it's kind of wild here. 0.9 bar, okay? So 0.9 repeating is actually equal to 1. When I first saw that when I was a kid, I was blown away. Infinite repeating decimal can actually be equal to a whole number. All right, and you can verify that too with an infinite geometric series if you want. Now this one I'm going to approach this one slightly different. So I'm just going to call the number n here. Okay, but notice 2 digits repeat. And since 2 digits repeats, I have to shift this decimal right 2 places. And to do that, I have to multiply by 100. So I'm going to multiply both sides by 100. And I shift the decimal right 2 places. Okay, so shift decimal right 2 places. 2 places right. Little key concept right there. Just going back to basic mathematics, we're going to subtract 100n minus 1n is 99n usually, okay? And when you subtract the decimals on the right, well, the infinite part cancels and you get 32, okay? So you get 32 here, and then you divide by 99. Ooh, here we go, and we're done. Okay, so right here, 32 divided by 99 is our result. So 0.32 repeating actually equals this fraction right here, this rational number. All right, let's verify it. So 32, all right, divided by 99. And notice it's the same thing. Okay, so there's two or three different methods, how to convert a repeating decimal to a rational number, to a fraction. All right, number 6. Number 6 is all about closure. Okay, in the beginning of the section 2, we talked about closure. So is the set of rationals Q, okay, let's highlight that part, is the set of rationals Q closed under the following operations? And justify your response with a proof or a counterexample. All right, so now the operation is this weird symbol. And this weird symbol here means that we're going to take whatever x and y are, divide them, and square it. Okay, so is this rational? Okay, so what we're going to do is let x and y be some rational number. So here we go. You're going to start exploring here. So if they're rational form. So you set let x equal to some rational number, a over b, okay, where a and b are integers. So a and b are integers. All right, and b is not equal to 0. We need two numbers, right? X and y are two different numbers. So let y equal to some different rational number. All right, where c and d are integers. Okay, again, they're rational, right? And d can't be equal to 0 either. So that's how you start. You pick two rational numbers for x and y. And then you go for it. So it says divide the two and square it. So here we go. So x, and this is a weird operation. It's not times, it's not subtraction, it's not a typical operation. It's whatever x is divided by y, quantity squared. So this right here is the operation. And what it tells you is it says divide them and square. That's what the operation tells you to do. So divide the numbers, divide, okay, and square. That's what the operation tells me. So x operated with y is equal to, okay, you got to take x divided by y. So a divided by b divided by c divided by d, and you got to square that puppy. Okay, now before we square it, whenever we divide fractions, you got to go back to grade school and you got to multiply by the reciprocal. So a divided by b times the reciprocal, d over c, and then squared. Simplifying a little bit, you got a times d divided by b times c. And when you square it, you square everything because these are products and quotients. So you square everything, a squared times d squared divided by b squared times c squared. Okay, and the question is this an integer over an integer? Okay, so is that the case? Well, let me see, a, b, c, and d, they're all integers. Okay, that's what I set up here. I set it up so that x and y are irrational, but because they're rational, a, b, c, and d are integers. Remember, this symbol here is integer. All right, z for Zalon. All right, integer set. And what we did learn in the first section is that when you take an integer squared, you get an integer. Okay, so we know that an integer, all right, times an integer is just another integer. Okay, we know that. So a squared, since it's equal to a times a, well, that's got to be an integer. And same thing for all the other ones. So d squared's got to be an integer. You know, because d times d is an integer times an integer, that's an integer. And then when you multiply two integers, you get an integer. So this is actually an integer divided by an integer. And because of that, it's rational. Okay, now what I just did was I took two general rational numbers. Okay, so these are my rational numbers right here. Those are rational. I operated with them, and this operation says take x and y with these two fractions, divide them and square it, and I got a rational number. And if it's closed, then the end result must be in the set, and it is, because I got a rational number. If I didn't get a rational number, then this would not be closed. All right, so this set is closed under this operation. So I can say, this is my conclusion, that this set is closed. So under the set of rationals, okay? So we're just going to make a little note, set is closed. Okay? Now sometimes it is and sometimes it isn't. You have to just test. Down here, this is a new operation. Okay, so this circle with a dot in it says take the reciprocal of x and reciprocal of y and add them together. Okay, so this is the operation. Again, it's not the typical operation, and we're not dealing with just straight multiplication, division, adding and subtracting. The operation says reciprocate both fractions and add. Okay, that's what the operation tells you in symbolically. Okay, x to the negative 1 is the reciprocal, so this means you got to reciprocate it. And this also says you have to take the reciprocal y, and then you have to add, okay, the reciprocals. Add the reciprocals. So I'm just translating the mathematical symbols into words so you understand what in the world's going on, because most people, when they get these problems here, have no idea what to do because they don't understand the symbols. So this new operation that you are looking at here says, okay, take x and y, reciprocate them, okay, invert them, and then add them. And if the result's still rational, then the set is closed under this operation. Okay, so and if it isn't rational, well, guess what? Then we're saying it's not closed. Okay, so here we go. So we're going to take these same two rational numbers above, and we're going to operate them. So let me detail this out. So here's the operation, the circle with a dot in it. So x operated with y is equal to x to the negative 1. Let me just rewrite it here so it's over here. X to the negative 1 plus y to the negative 1, which is just the reciprocal. Okay, so we take our first fraction, a divided by b to the negative 1 power, plus c divided by d to the negative 1 power, which is just the reciprocal. So I get b over a plus d over c. Notice I just reciprocated those. All right, and then you got to combine your fractions. Okay, so let's combine fractions. So let's get a common denominator here by using the other denominator. We need an LCD. Okay, so here we go. And this is equal to b times c over ac plus d times a over ca. And guess what? They have common denominators. So this is bc plus da. Okay, I simply add the numerators divided by ac. Again, common denominators, bc plus dA is the new numerator divided by the common denominator, okay? AC and CA are the same. Those are the common denominators. So the question is this a rational number? Okay, is this rational number? Question mark. Okay, so is an integer times an integer an integer? And we said up here it is, because we know that from the previous section. So this is an integer, this is an integer, and this is an integer. And we already know that an integer plus an integer is an integer. Up here I said an integer times an integer is an integer. We know that from previously. But we also know that an integer plus an integer is just an integer. So we have an integer divided by an integer. Guess what? And that's rational form. Okay? So this set is closed under this operation. So set is closed. Okay, under this weird operation circle dot. Okay, circle dot. The previous one, it's closed under circle cross right here under this new operating system. Okay, so it's just a weird symbol dealing with a new operation. Takes some getting used to, so you might have to listen to this again. So rewind the video and listen through it entirely again and see if you can understand it again. I'm taking all the basics that we've learned about closure from the last two sections. Okay. Oh, here's another proof on closure, okay, about even numbers. So if n is an even number, then n cubed is also even. So we have to, what's even form? So let's talk about that. So even form. Now this goes back to section 1, I think. So you might have to take out your notes to section 1. Okay. So if you don't remember what that is, n is equal to 2k, where k is an integer. So k is an element of z. Okay, it's an integer set. The reason why is because like 8 is 2 times 4, right? Where 4 is an integer. 10 is 2 times 5. Any even number can be expressed as 2 times some integer. So even form is 2 times an integer. So n is equal to 2 times, some integer. That's even form. Okay, having said that, here we go. So let's take that integer, and which is 2k, and let's cube it. So if you cube an even, do you get an even? That's the question. If you get an even, if you cube an even and you get an even, and then it's closed. If you cube an even and we get an odd, then it's not closed. All right, so here's the proof. Here we go. I'm going to prove it. I think it's going to be even, because if you take like 4 and cube it, you get 64, which is even. If you take 2 and cube it, you get 8, and an 8 is even. So if you want to explore a little bit, like given, let's say, n equal to 2, okay, well then n cubed, excuse me, let me do a little exploration here. So n cubed is 2 cubed, which is 8, okay? And notice that we start off with an even, you get an even. When n equals 4, then n cubed is equal to 4 cubed, which is 64. So you start off with an even, you get an even. So I'm going to prove this because I think it's true. So again, you got to explore a little bit first and test it. I think it's going to be closed because n cubed is always going to be even. So that's my conjecture. So n cubed is always even. And that's one thing to think it. It's another thing to prove it. So let's prove it. So here's the proof. All right, you're going to take a number like n, which is 2k. So, and you're going to cube it. So n cubed is equal to 2k cubed, which is 2 cubed times k cubed. You got to cube everything, which is 8 times k cubed. Okay, and you have to show that's even. So you just have to rewrite it here. We know that 8 is 2 times 4. Right, so I'm just going to factor that. So 2 times 4k cubed. I'm just going to rewrite it just so you can see it better here. So 2 times a quantity, all right, 4k cubed. So is this in even form? Let me highlight it. Even form is right here. 2 times an integer. Well, is k cubed an integer? Is it integer times an integer and an integer? So is that an integer? Question mark. And the answer is yes, because k cubed is nothing more than k times k times k. And we know that integer times an integer times an integer is an integer. Okay? And the integer times 4 is still another integer. So this is 2 times an integer, which is even form. And because of that, this set is closed. All right, so the set is closed. That's my final conclusion, because when you cube an even, you get an even. All right. So basically, it's a true statement. Okay. In simple words. Okay, that's true. When you have an even number and you cube an even number, it's also even. All right. Rock and roll. Now we're dealing with another section here. So find 3 rational numbers between 5/9 and 5/8. What lesson was this? Let's go back and let's find out. I forget all the numbers sometimes. So 2C, let's see. Oh yeah, it's 2C1, I think. Yes. 2C1. Okay, so let's note that. Okay, so this is activity 2C1. All right, so get out your notes, you guys. Find 3 rational numbers between these two guys. And there's different ways of doing this. Okay, there's 2 methods possible. So let's make a little note here. So 2 methods possible, at least 2 that we discussed. There might be more than 2. Okay, so notice that the numerator is the same. So 5/9, and then we have to find 3 numbers between these two guys. So I'm going to use decimals. So again, so you can use any method you want. So using decimals, okay, I'm going to rewrite this as I'm going to pick something between 8 and 9. So let's focus in on the denominators here. So I'm going to say 5 between 8 and 9 is like 8.5, and smaller than that would be 8.4, let's say, and another one would be 8.1. Okay, those are 3 numbers in between the 5/9 and 5/8. All right, but they're not rational, so you got to rationalize and make them rational, because it says rational numbers here, guys. So make them rational. Okay, which means an integer divided by an integer. Okay, and we don't have an integer divided by an integer. This right here is not an integer, if you guys recall. Okay, so to do that, let's go for it. So 5 divided by 8.5. I'm just going to multiply it by 10/10, and I get 50 divided by 85, and then you simplify it, and you divide by 5, and you get 1 divided by, I don't know, 17 maybe. 85 divided by 5 is 17. Okay, so there's one result. The next one, 5 divided by 8.4, multiplied by 10/10. That's only, you don't have to. You can do it other ways. You can double it if you want. So divided by this, but this is easier for most people. Divide both by 2, so you get 25 divided by 42. And the last one, 5 divided by 8.1. So on this one here, again, you don't have to multiply by 10/10. You can multiply it just simply by 2. Okay, it's totally up to you. So you get 50 divided by 81. That can't be simplified. So you're done. So what are the results? Okay, 10/17, 25 40 seconds, 50 81st. Okay, these are between these two fractions. Okay, between the 5/9 and 5/8. Okay, those are my end results. All right. So what is the average? The average, okay, to get an average of two numbers, okay, you got to take the sum, divide by 2, or you can read it as half the sum. Same thing. Okay, so the average in this case is 1/2 of 3/5 and 3/4. Notice that you don't have common denominators here, so let's get common denominators. I don't know why that blacked out there. So this is 1/2 times 12/20 plus 15/20. And so 12 and 15 is usually 27. So 27/20. And that's 27/40. Okay, so there's the average. Where does it lie? On the number line in respect to these two guys, it's in the middle. Okay, the average is a middle number. Okay. Okay, you can verify that. Okay, so the average always lies in the middle. Okay, always lies in the middle or in the center. Okay, so now the next one here, find three rational numbers that are, between 1/4 and 0.3 repeating. Okay, so what is that? Well, 0.3 repeating is 1/3. So it's kind of like question 8 right here. So 8 and 10 are similar. Okay, similar. Okay, so let's do that. Let's get these done. So let's kind of set it up. Oops. 3. All right, so you can get common denominators if you want. If you want to do that, then that would be 12. So this is 3/12, and this is 4/12. So if you want to use common denominators, you can, but you're going to have a fun time in here because between 3 and 4, there aren't too many whole numbers. So I wouldn't do this method here. I wouldn't use the LCD approach. Okay, I would use the decimals. So using decimals probably be a little bit easier here. So I would start off by taking 1 divided by 3.5, let's say, 1 divided by 3.3, and then 1 divided by maybe 3.1. So I focused in on the denominators here. Between 3 and 4 are these 3 decimals here. And then you just have to massage a little bit and then make them rational, like I said over here. So refer to number 8. So make them rational. Okay, so here we go. So let's make them rational. So 1 divided by 3.5, so multiply by 10/10, and you get 10/35. Reduce that, divide by 5, you get 2/7. So 1 divided by 3.3, multiply by 10/10, and you get 10/33. That can't be simplified. And the last one, 1 divided by 3.1. Same method as above in number 8, multiply by 10/10, and you get 10/31, and you are done. So the 3 fractions that lie between these are 2/7, 10/33, and 10/31. Okay? So I think decimals, you can get creative and use decimals. You can use the LCD approach too. Okay? Make a little note of that. Okay, so the LCD approach can also be used. All right, it can also be used. Totally up to you. Okay. All right, now the next portion are all constructions. Oh, actually, no. I'm sorry. Number 11 we can do. 12 are constructions. So right through here, these are constructions, and I can't do it on this video right here, so I'm going to make another video. So on this one here, on number 12 down, look for review video part 2. Okay? And that will come later. Right now, let's work in number 11, because I could do that. That's no problem. So determine the location of 0 on the number line given the two fractions. Okay, so notice that 7 is a factor of 21. Okay, so I'm just going to get common denominators here. So if I multiply this by 3/3, so negative 2/7 times 3/3 is negative 6/21. So there's my equivalent fraction right here. And so what you want to do is figure out, at least the way I would do it, I would figure out the distance between the two. Okay, so I'm talking about this distance right here. What is that distance? So between negative 6/21 and 2/21 is the distance of 8/21. So note, so 6/21 plus 2/21, because 0 is somewhere in the middle here. All right, is 8/21. So there's your distance between the two. So I'm going to note that. So distance is 8/21 between the two. And if we break that up into parts, we might be able to figure out the location of 0. Now 2/21, that's even. So if I break 8 up into 4 equal parts, we'll get 2/21. So let me break it up into 4 equal parts, see if it can make this happen here. So divide into 4 equal parts. So if we count by 2/21, so this would be 0 here, and then negative 4/21, and then negative 2/21, negative 2/21, and then this would be negative 4/21, and then the next one would be negative 6/21. So 0, okay, is right here. So you have to divide this segment, this distance here between the two given fractions into 4 equal parts. So that was the key. So divide into 4 equal parts. And the way I thought about that, or the reason why I thought about that, is because 2 and 6 are even, 8's even. So I was thinking, 8 is a multiple of 2. How many multiples of 2 is 8? Well, it's 4. And so I broke it up into 4 equal parts, and I found 0. Okay, now how about this one here? Find the location of 0. Okay, so where would it be? Okay, so obviously these are both negative, and so 0's got to be to the right of negative 1/6. Okay, get common denominators here. So let's do that first. So negative 1/2. If you the common denominator is 6, so multiply by 3/3, and I get negative 3/6 here. So this is the same thing as negative 3/6. Okay, so if we count by 1/6, we should be able to figure out where 0 is. So in the middle here is negative 2/6, negative 3/6, negative 2/6, and then if you go to the right, okay, again, equal spacing here. So these parts are equal. So this is in the middle here. Let me erase this. So I bisected that first. It's in the middle. It's the middle of negative 1/6 and negative 3/6. So put that in the middle, and then equally space them. So this distance is 1/6. This is 1/6. This is 1/6. So this should be 0. So there we go. The goal is to find 0 in this activity. All right. So I made common denominators, and then I used that. So one of the key things that you have to do in this activity is to use common denominators. Not the only way to do this. This was done in a previous activity. I think it was like 2A1 or 2A2. Let's find out. I forget which activity that was in. So, oh, wrong class. Okay, so... So to be... Oh, maybe it was 2B5, 2B2, and 2B5. Let's see. Not 2B2, 2B5. Yep. So this is respect to 2B5. So let's make a little note of that. So activity 2B5. Okay. Okay, so I told you guys what sections to look for, and I also helped you out with the review here. I will work out the constructions in my next video here, since I can't do it on my laptop. And then and you put the two together and get ready for your test next week. And remember, this is a video, right? So because it is, use it to your advantage, all right? Go back and rewind and listen to any part that you need to go over again, because sometimes it takes, a few, people more than one viewing. And so identify the things that were tough for you, go back and identify them, mark them, tag them with sticky notes, and practice. That's what I used to do. I used to practice like a madman. So I used to figure it out, talk to my instructor if I need to, use different resources. We didn't have videos back in my day, but I went to the instructor. You just use my videos because we're online now. And then practice like a madman. Identify the hard ones. Like if number 3 is hard for you, practice 3A and B like 3 or 4 times each until it becomes easy. All right. Usually perfect practice does people a lot of good. Okay. Practice doesn't make perfect, but perfect practice does. So make sure you check it and do it right, and check it with my work here, and go for it. Test is next week, so make yourself proud, okay, because nothing comes free. I don't care. I'm old-fashioned here, but I believe practice or good grades come through a lot of practice, a lot of preparation. So make yourself proud. And I will see you in my next lesson. This is Ainsworth. Bye-bye.